Okay, let's look at specifics of acid-base titrations. Please read the textbook chapters related to this. First, indicators. What happens to indicator when it changes color? Phenolphthalein changes color from colorless to red pinkish. Colorless means you simply do not see the absorption band in UV area. So deprotonation of phenolphthalein molecule results in change of electron structure and as a result changes color of each form. Same is true for brim-cresol green. The formulas are very similar. The difference is sulfonic group and carboxylic group here, and the color changes from yellow to blue now, which is much easier to handle. The role of sulfur and carboxylic groups is to increase the solubility of your indicator. If it is insoluble in water, it would be useless. It can be different type of structures, so diazo bonds with nitrogen-nitrogen double bond change color from pinkish red to yellow, and these are methyl orange and methyl red indicators, very popular in analytical chemistry. So what do we see? An indicator is an acid, so it has its own pK, and this pK you have exactly the same amount of each form of indicator. Red and yellow mixing together, giving something like orange. This is the place where you want to stop your titration. Now we can look at Henderson-Hasselbalch equation and see that if we have ratio basic form to acidic 10 to 1, pH will be pK plus 1. If ratio will be 1 to 10, you'll have pH equal to pK minus 1. 10 to 1 and 1 to 10 are convenient approximates for the highest and lowest pH you can see with this indicator. So when you have 90% of yellow form and only 10% of red form, you will not see any red, you'll see just yellow. And at any pH above this, you'll see yellow again. If you'll have only 10% of yellow and 90% of red, you'll see red and will not see any hue of yellow. So what happens? When you're coming 1 unit of pH close to pK, you start to change this from yellow to red. So you see something yellow, more reddish, orange in the middle. Again, this is a place where you want to stop. And then different hues of red until you have pink red at pK a minus 1. And after that, you see no changes. So the whole scale of pH change with one indicator is pK plus minus 1, 2 units of pH. In fact, the transition range was determined experimentally for most convenient indicators we have used. It slightly differs from pK plus minus 1 because colors have different sensitivity for human eye. So we have different indicators that are suitable for pH starting from 0 all the way to neutral, and then another group of indicators can be used for pHs an area from neutral all the way to highly basic. Preparation of indicators is usually very straightforward. We prepare 0.1% solution in water or sometimes in alcohol. So what happens when I titrate sodium hydroxide with hydrochloric acid? At starting point I have strongly basic pH, then pH is slowly going down until I am very close to equivalence point. When I am very close to equivalence point, pH dramatically drops down from very basic to very acidic. On this chart you can see where different indicators will change color. If you have very large drop of pH, most of indicators will be suitable. If you'll stop at this point, you'll over-titrate only by 0.1% relative, so your error will be fantastically small. If you under-titrate, in this case with phenolphthalein, you still will be within 0.1% relative error from your theoretical point, so you'll not be able to detect it with your burette. Story is different when you titrate weak acid or with strong base. In this case, your equivalence point will be weak base, and it will be located far away from neutral 7. As a result, if you'll use wrong indicators like this group, you'll stop at pH that is far away from equivalence point. You need to pick up the proper indicator like phenolphthalein in this case, and yes, your error will be still acceptable and less than 0.1%. The general rule is if you run a strong acid, titration jump is very high and most of indicators will be suitable. If you have slightly weaker acid, jump is smaller. With pKs around 6, it's becoming very small. And when you're reaching pK 8, practically you can never receive precision of 0.1%. With pK 10 and above, you cannot titrate at all. Same is true for different concentrations of acid. If you titrate relatively large concentrations, you have visible jump. But with dilution, you have gradual decrease of jump, and for very diluted solutions, you do not have any pH jump at all. That means you should avoid unnecessary dilution of your solutions with water when you titrate. Same is true with any other solvent. Anyway, titration is a little bit tricky when you are using color indicators because they change color in a range of pH values. It's much easier to do with the pH indicator, which will be glass electrode or any other electrode that will directly measure pH value and provide you with the numbers. Practically all modern pH meters, devices to measure pH, will be digital. So, as a result, you are getting plenty of points. With automatic titrator, you'll have several hundreds of points that will relate volume of your titrate to pH value of your solution. You can see there are two jumps on this plot. So how we can figure out where to stop at each of these jumps? When you're looking at raw data, it's a little bit tricky. Much more suitable is looking at derivatives. What stands for derivative? Just a reminder. This is the slope of your curve. So there is low slope in this area, then you have jump. The slope is becoming large. Then you have kind of small plateau, is not exactly plateau, but slope is much lower. And then you have the second jump, after which the curve is coming to real plateau. As a result, the slope will go up and it will have maximum at first inflection point, then will go down and again reach second maximum, after which it will decline. You can also measure second derivative. We'll never do that here. Now, how we do derivation? We actually never do it. What we do, we take difference between 2 points we have measured, and this will be our difference here. Then we look at difference in pH values and put it above the line. So instead of dpH over dV, we have delta pH, change of pH, versus change of volume. As you can see, the numbers are different and maximum is visibly located here. You can also take change of changes and then you'll have second derivative. Second derivative changes sign when you have maximum. So they were positive here, they're negative there. And this is the way we do all our titrations with automatic titrators. The approach is convenient because you process data after you did titration. You are not afraid to over titrate because you have your results on your computer and you can recalculate them anytime.